Welcome to an interactive course designed to validate and improve our knowledge of heat treatment. The topic of this course is steel designation. Steel's designation is very complicated because there is no unified international system. That is why this publication, which is called Stahlschlüssel, lists more than 70,000 steel grades from 300 suppliers, including their equivalents. Although they are sometimes the same or similar, each has a different marking depending on whether they are made according to the American or German or British, French, or Japanese standards. Of course, this category also includes the designation of steels according to Czech specifications, which is still established and still lives its own life. In addition, designation according to European standards or marking of steels according to the practices established by steel manufacturers such as Böhler, Uddeholm, Aubert Duval, Kind and Company, and others, is very difficult for the untrained user. So orientation in steel marking is very confusing. The question is why we should actually know the designation of steels. The answer is simple. We have to be able to understand the customer's requirements. We must be able to recognize which heat treatment should be applied in order to achieve the desired properties. Here are some examples of what the material recipe looks like on a drawing. Since a number of drawings are from different foreign manufacturers, the specification of the material is very diverse. Marking according to Czech standards still occurs, especially in old drawings, but they need to be taken with caution. In this case, the specification of 19552 steel leads to the question of whether it is really this steel or 1.2343 or H11 steel. It must be taken into account that local Czech standards have already been cancelled and replaced by European standards. At least a minimum knowledge of material designation is a must for heat treaters, as it is a tool for them to specify heat treatment procedures to meet customer expectations. It is not easy with national standards at the moment. They have been gradually cancelled since 1988 and replaced by standards based on the European EN standards. These are the standards EN 120, Definition and Classification of Grades of Steels, EN 127-1, Steel Designation Systems, Part 1, Steel Names, and EN 127-2, Steel Designation Systems, Part 2, Steel Numbers. The first part contains a regulation on how to create a steel name based on mechanical or physical properties, and the second on how to create a numerical code for a new steel. Both are now managed by the European Steel Registration Office. However, the basis for this new standards was the original DN standard, which is completely different from, for example, the original Czech standard. However, since a lot of drawings according to this old designation still exist, it is necessary to know both the original number or name and the new one. The order of importance of the individual standards is shown in this pyramid of importance. The ISO standards, which are valid internationally, are seemingly at the highest level. They are immediately followed by European or national standards. However, in heat treatment, it works the other way around. If there are company or internal customer standards, such as SNECMA, Safran for the aerospace industry, Volkswagen for the automotive industry, these standards have the highest priority. Next are the specifications of steel manufacturers, if their origin is known, and only if not, do national standards follow. According to EN or ISO standards, heat treatment will only be applied if it is explicitly stated in the sales order. For example, if we have an order for the processing of AISI 4140 steel, then its heat treatment must be carried out according to the American standard. If the order is for the heat treatment of 42 chromium molybdenum for steel, then the procedures must be set according to the European EN standard, and this even if both of these steels are almost identical. So, in order to assign the correct heat treatment process to a material, we must first examine its use, if there is a company standard or industry standard that the heat treatment must comply with, and if there is not, then we must also examine the origin of the steel grade, because in that case the heat treatment process will have to comply with the steel manufacturer's regulations. And if neither one nor the other exists, then we can only turn to the general national or international standards for the given material. In any case, we must record the sales order with the material code or name according to the order or drawing or other received documentation, and we must not record it with the material equivalent, even if it usually exists. As already mentioned, we have three standards specifying material designations. The first is EN 1020. It is essentially superior to EN 102741 and 102722, and it says what types of steel we have. For example, unalloyed, alloyed, stainless, or tool steels. So it is a standard that establishes the basic terminology and steel classification according to chemical composition and properties. It does not provide specific marks or numerical designations, only a classification framework. The standard EN 1027-1 Designation Systems for Steels, Part 1. Steel names, principal symbol establishes the naming of steels like S235JR, 16 chromium manganese 5, and defines how symbolic marks are created according to mechanical properties, use, or chemical composition. The standard EN 1027-2 Designation Systems for Steels, Part 2, Numerical Systems, defines numerical designations for steels, material numbers, for example 1.008 for S235JR steel, which are unambiguous and language independent, and which can be used for material databases, spreadsheets, and international trade. This table shows how all three standards affect the designation of steels. First, the description according to EN 120. Second, the name expressing the purpose, mechanical properties or chemical composition. And last one, the numerical code. The EN 120 standard also uses another classification of steels. In addition to the classification of steels into alloyed and unalloyed, it also distinguishes steels into steels with usual properties, unalloyed quality steels, unalloyed special steels, alloyed quality steels, and alloyed special steels. However, not all types of steels are of interest in the heat treatment process. We will only be interested in alloyed steels, and then alloyed quality steels, and alloyed special steels. These will be the subject of possible heat treatment. Whether a steel belongs to the group of unalloyed or alloyed steels is decided according to this table. It shows the limits of alloying elements for this specification. Unalloyed steels are all steels where none of the elements in the table exceed the limit values. If at least one element exceeds this value, then it is alloyed quality steel. Alloyed special steels are steels where the required values are achieved by heat treatment, guaranteed precise chemical composition, compliance with production processes, and testing procedures. This is exactly the group of steels that is of interest to heat treaters and heat treatment plants. For designation purposes, the standard classifies steels into four categories. Group 1, unalloyed steels with manganese content less than 1%. Group 2, unalloyed steels with manganese higher than 1. Or steels where all alloying elements are up to 5%. Group 3, alloyed steels where at least one element is only above 5%. And Group 4, alloyed high-speed steels. Standard EN 100-27-1 sets out the basic rules for determining the name of steel according to its intended use. The name of the steel contains several details. The letter G is indicated if it is cast steel. If it is steel, the space is left blank. The next letter in the name refers to the purpose of use. The content of these letter symbols is in the standard. Only basic examples are given here. The number after the letter expresses certain mechanical properties of the steel related to this letter. Its meaning therefore changes depending on the steel category. In our case, for example, steel marked S, it is structural steel, and the number 235 indicates the minimum yield strength. In other cases, however, it may be the minimum or nominal tensile strength. The numerical symbol is followed by a number of additional symbols expressing the guaranteed mechanical properties of the steel. In the case of structural steels of category S, it is the guaranteed impact strength with the designation according to the table in the standard. The following is the category of symbols related to further detailed differentiation. For steel of category S, these characters can take on values from G1 to G4. In our case, the symbol G2 means steel, that is non-rimming and suitable for welding. The last additional character can be, for example, the symbol +N. Then it is also normalized steel, or +Q for hardened steel. The first example is steel, 1.1545. Since it is not cast steel, the letter G is omitted. According to EN, for carbon steels, the initial character is the letter C. Next is a number that represents a 100-fold value of the carbon content. So if the steel has 1.05% of carbon, then the number will be 105. Additional letters after the number express the purpose of using the steel or its properties. The letter U means that it is a tool steel. The steel mark C105U therefore says that it is a carbon steel with a carbon content of 1.05%, which is suitable for the production of tools. The same will be true for steel 1.1191, according to ENC45E. Since it is a carbon steel, we will again start with the letter C. A carbon content of 0.45% is multiplied by 100, and this gives a value of 45. And the attached letter E means that it will be a steel with limited sulfur content. The second category of steels are low alloy steels with alloying elements up to 5%, or unalloyed steels with a manganese content above 1%. With these steels, it is even more complicated. The type of steel does not start with a letter, but with a number that indicates the carbon content. An exception would be steels for castings, starting with the letter G. For these steels, individual alloying elements are listed, expressed by a number according to the table. The main alloys, chromium, cobalt, manganese, nickel, silicon or tungsten, are multiplied by a coefficient of 4, the other elements by 10, the others by 100, and the content of the element boron by 1000. The alloying elements are listed in the order in which they appear in the table. For example, chrome vanadium steel 1.8159. Its chemical composition is as follows. The steel has a carbon content of 0.51%, 1.1% chromium, and 0.17% vanadium. Its EN designation will be 100 times the carbon, which is 51. Then the alloying elements chromium and vanadium will be listed, and 4 times the chromium content. 4 times 1.1 equals 4.4. This number is rounded down to the digit 4. Vanadium will not be listed numerically, since its 4 times amount is less than 1%. The steel will therefore be designated 51 chromium vanadium 4. Another example is case-hardened steel, 1.5918. Its chemical composition is approximately 0.17% carbon, 1.5% chromium, and 1.5% nickel. The designation will again be 100 times the carbon value. Then the elements chromium and nickel will be listed, and 4 times the amount of chromium and nickel calculated as a result of 6. The final designation of the steel is 17 chromium nickel 66. The third category of steels are high alloy steels with a minimum content of at least one element over 5%. This series of steels is defined by the letter X. This letter may be preceded by the letter G for cast steels or PM for powder steels. For example, today's frequently used steel 1.2379. Its chemical composition is approximately 1.53% carbon, 12% chromium, molybdenum 0.9%, as well as vanadium. The steel designation will therefore begin with the letter X. 100 times the carbon content is expressed by the number 153. The alloying elements, chromium, molybdenum, and vanadium, are then listed. And finally, a number must be added expressing the alloy content in percent. In the case of chromium, this is 12%. Other alloys are up to 1%, and therefore their number will not be indicated. The final steel designation will therefore be X153 chromium molybdenum vanadium 12. Similarly, steel 1.2343. The letter X means that it is an alloy steel. The number 37 represents the carbon content and chromium molybdenum vanadium, the main alloying elements. The number 5 to 1 says that the steel has 5% chromium and about 1% molybdenum. The resulting steel grade will be X37 chromium molybdenum vanadium 5-1. The last category is high-speed steels. Their designation is with the letters HS, and then the average values of the alloys are given in the order of tungsten, molybdenum, vanadium, and cobalt. For example, in the case of steel 1.3343, the steel name will start with the letters HS, followed by the numbers 652. These say that the steel has 6% tungsten, 5% molybdenum, and 2% vanadium. If we add the letter C, then it would mean that it is cold-rolled steel. As a result, it will be HS6252C steel. If the letters HS are preceded by code PM, then it will be powder high-speed steel. In addition to designating steels according to their purpose or chemical composition, EN standards also specify steels by means of a numerical code. This method of designating consists of using a number that defines the main material group. If the number 1 is given, it is steel. The meanings of the other numerical codes are given in the table. The relevant steel group is given in the following two places. The meaning of the individual numerical groups is specified in EN 100 27-2, and the detailed structure of the numbers will be explained later. The numerical codes are in each case based on the original DIN standard, and are in most cases identical to this historic German standard. They were previously known as Werkstoffnummer. The last two numbers in the material code are the sequence numbers within the group. There are two more numbers in brackets, but these are reserved for future and are not currently used. This figure shows an overview table of all codes. As already explained, there are both unalloyed steels, quality and special, and alloyed steels, quality and special. The categorization is clearly stated in the table header. In some cases, the table shows that no steel has yet been specified or developed for a given steel group or alloying element combination. In the case of the previously mentioned steel 1.3343, it can be seen that this steel falls into group 33, cobalt-free high-speed steels. The first category of numbers are steels falling into groups 00 to 19. These are unalloyed steels with usual properties. Unalloyed quality steels are numbered with numbers 00 to 09. In groups 10 to 19, they are unalloyed special steels. The C105U steel we are discussing, although it is a tool steel, is classified according to the European standard in the class of unalloyed special steels, with group number 15, tool steels, and designation 1.1545. All alloyed special steels are numerically classified into categories 20 to 89. In this table, the steels are classified according to the category and combination of alloying elements, or their percentage, into different groups, which are distinguished by a numerical code representing the first two digits after the dot. The basic groups of special steels are split into categories: 20 to 29, tool steels, 30 to 39, miscellaneous steels, 40 to 49, stainless steels and heat-resistant steels, 50 to 89, structural steels, steels for pressure vessels, and engineering steels. The numerical codes are based on the original DIN standard and are in most cases identical to this historical standard. They were previously known as Werkstoff number. As mentioned in the introduction, when determining the equivalent, it is primarily a matter of similarity of steels, not 100% conformity. National standards may differ from these international ones. Therefore, if steel is specified according to EN, it is more correct to follow the procedures proposed for this standard within the framework of EN standards. In case of replacing the prescribed steel designation with a national standard, non-conforming behavior and non-conforming heat treatment results cannot be excluded. An example can be seen in this table, where for a number of steel grades in Czech national standards, there is no equivalent at all. On the one hand, it is a consequence of the historical development of steels in a given country. On the other hand, it is evidence of the continuous development of new steel grades, with designation according to EN, which will never have an equivalent according to national standards that have been cancelled in the EU. A special category of steel designation is their coding by the manufacturer's trade name. For some steel manufacturers, this naming has a certain logic either in the letter designation or in the name or number. In many cases, however, this is not the case. For example, the Swedish steel manufacturer Uddeholm. Its hot work steels, such as Dievar or QRO90, have long been used by both tool designers and tool manufacturers, but they have nothing in common with the EN designation. In the case of their heat treatment, it is therefore necessary to proceed strictly according to the recommendations of the steel manufacturer, and not according to general standards, both international and national. This is very important, because in some cases, these steels with trade names do not have an equivalent in EN. A striking example is Dievar steel, which is currently used for high-pressure die casting dies. If this steel grade is indicated on the drawing, the heat treater is obliged to proceed according to the Uddeholm regulations for this steel grade. However, if the steel is intended for die casting dies, then this does not apply either, because both the tool manufacturer and the heat treater must proceed strictly according to NADCA 207, which is the North American Dies Casting Association specification for the production of die casting dies. At the same time, it is necessary to take into account the recommendations according to CQI 27, Casting System Assessment, for die casting parts for the automotive industry. Other companies take a similar approach, for example Böhler. Although it assigns a number to each steel, fortunately, it also has another distinction for steel groups by a letter that expresses the area of application. For example, K stands for a group of steels for cold work, W, a group of steels for hot work, N is stainless steels, M is steel for plastic molds, or S for high-speed steels. Another distinction between steels is in the remelting process. Isodisc steels are non-remelted. Isoblock, Isodur, Isorapid, and Isoplast steels are remelted under slag, and VMR steels are remelted in vacuum. However, for the heat treater, if the manufacturer's steel grade name is stated in the drawing, it must be followed by the Böhler regulation for this material, although in some cases there is an equivalent according to EN. For example, steels W300 or W302 have their equivalents, but heat treatment should be carried out according to the Böhler regulation. However, as can be seen from the table, some steels completely deviate from the EN designation and therefore have no equivalent. See, for example, W350 or W360 steels. As is clear from the previous information, steel designation is complicated due to the fact that there are too many designation systems. As new manufacturers of steels or steel parts appear, so do their drawings, and therefore steel grades. It is therefore not important to remember these numbers or names, but to find sufficient documentation for them, so that heat treatment can be carried out according to the usual procedures. So where can we find them? This problem is best addressed in the already mentioned publication, Stahlschlüssel. It can be found at this address and either purchased in book form or used in the online version. From the point of view of EN standards, the best search is on the European Steel and Alloy Grades website. This website is for free. The Total Materia publication is also interesting, but it is a paid application, which is always a problem. When it comes to company materials, all steel suppliers offer them on their websites and are usually sufficient to reliably determine heat treatment procedures. The biggest problem is the availability of professional guidelines such as Internal Aerospace Standards or NADCA 207. However, aerospace standards are not available or are only accessible to aerospace suppliers, usually after being registered in the NADCAP supplier list or after signing a non-disclosure agreement. However, they contain really detailed procedures because all suppliers must follow these procedures without exception. Therefore, these standards are superior to all others. The NADCA 207 specification, intended for manufacturers and users of die casting tools, can be downloaded for $100 at this address. An interesting application is Steel Navigator. If we don't know what to do at all, we can enter the chemical composition of the steel here, and the application will calculate the tempering curves, the Jomini hardenability diagram for water, oil, or air, and we will also get a simplified CCT diagram. The steel designation course is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels, so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So, thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website, jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to ASCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a permanent license for €500 per course. The compressed zip file will be 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0 on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, at home, and you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.